We are moving on with Chapter 14, our chapter on sound. We're currently on slide 55 for the Doppler effect. So when we're talking about the Doppler effect, we've all experienced the Doppler effect before, just perhaps not been able to put a name to the phenomenon that we experience. We've all encountered some type of alarm that moves towards and away from us, whether it be from a police siren or an ambulance or a fire truck. Think about what happens, what you hear as the siren comes towards you. How does it change when it's next to you? And then how is that pitch, that frequency that you're experiencing, changing as that siren moves away from you? So we're going to think about this talking about an ambulance, for instance. And as this ambulance, we're standing outside, this ambulance moves towards us. It continually emits sound waves at certain frequencies. This happens all the while moving toward those sound waves that are emitted from the alarm. As the ambulance moves toward you, it compresses those sound waves, making you hear a higher pitched sound as the ambulance moves in your direction. Once the ambulance moves away from you, the sound waves are farther apart, so you hear a sound wave with a lower pitch and a smaller frequency. Remember, pitch and frequency are directly related. So when we talk about the Doppler effect, we're talking about all in terms of relative motion. So if there is relative motion between a sound source and an observer, the source and the observer are going to be key when we're discussing this here. The observer will detect a frequency which is different from the frequency of the source. This phenomenon is called the Doppler effect. I posted a couple of different videos, some funny videos of the Doppler effect on Google Classroom. Definitely check them out. It will help you to visualize and experience the Doppler effect a little bit better. So generally, if the source and the observer are moving toward each other, the observed frequency is higher than the source frequency. What you have to remember is that the frequency, the pitch that you're hearing, is not actually changing. It's not like as the train whistle, which is actually going on outside of my window right now, is changing as it moves towards you. Those sound waves are compressing, making you experience a change in the apparent frequency. If the source and the observer are moving away from each other, the observed frequency is lower than the source frequency. So spherical waves can be represented with a series of circular arcs, which correspond to lines of maximum intensity. Arcs are called wave fronts. Radial lines pointing outward that are perpendicular to your arcs are called rays. So when you look at this second picture here, we have the wave fronts that are arced, and the rays represented by these arrows are perpendicular to those wave fronts. So as we talk about the Doppler effect, we're going to talk about a couple of different cases. When we're talking about this, we're assuming air is stationary and all speed measurements are made relative to the stationary medium. So when moving towards the source, an observer moves at a distance of v naught times t in t seconds. The observer detects an additional number of wave fronts, which is equal to the distance traveled divided by your wavelength. The frequency heard by the observer increases. So this bottom formula right here, this says that the frequency of your observer, here's your formula, is equal to the frequency of the source multiplied by the speed of the wave plus the speed of the observer divided by the speed of your wave. When we look at an observer moving relative to a stationary source, we have an observer that is moving away from this source. This means that your frequency is going to decrease. Notice here how your formula changes. If I go back one, if you notice on the formula down here, your velocity of the wave plus your observer are added together. In this situation, your velocity of your wave and of your observer are subtracted. This is when an observer moves away from your source. So for the second case, we have a source that's moving toward an observer that is at rest, or your stationary observer. The observed frequency increases when the source is moving toward your observer, as you can see in this picture right here. Again, your sound waves that are going to compress rather than be spread apart near observer B. Oh, as I put all of these formulas up here for you, the bottom formula here is your formula that we have to be able to solve for this. The frequency of the observer is equal to the frequency of the source multiplied by the speed of your wave divided by the speed of your wave minus the speed of your source. We're taking into account the different wavelengths of the observer and the source. We're taking into account the different frequencies. Your formula is this bottom formula here. A lot of people say that you can, or I should say a lot of physicists will say, that you can just take this general case formula, and if you know this general case, you're able to deduce all of the other ones. The thing with this, you have to be careful with your signs. So as you're going through and reading this slide here, the signs for the values substituted for your velocity of your observer and the velocity of the source depend on the direction of your velocity. When the observer moves toward your source, a positive speed is substituted for v of the observer. When the observer moves away from the source, a negative speed is substituted for v of the observer. Similarly, a positive speed is substituted for the speed of the source when the source moves toward the observer, and a negative speed when the source moves away from the observer. You have to be careful with your signs. So you can either go through and know all of the other cases, or you can stick with this general case and then see what happens as you go through each problem depending on what direction you're moving. I am going to post a video of going over all of the different problems, and I will do my very best to explain each problem. So follow along with that video as you're going through to go over the problems that go with this chapter. So sound waves bunch up in front of a moving source. We already talked about that, being that they are going to compress, giving a higher frequency. Again, frequency and pitch are directly related. The more spread out, the more distance you have between your waves, the lower the frequency, the lower the pitch. So we can talk about the Doppler effect in a couple of different situations. So the first being radar, the way that police will see if you're speeding. And truthfully, by the time, because we're talking about waves and waves travel a very far distance, by the time that you see the police officer sitting on the side, they already know that you were speeding. So a lot of times people will slow down when they see a cop car, thinking that, they see them and they slow down. But ultimately, they've already detected if you're speeding or not. So radar use radio waves that are emitted, reflected, and then come back to your gun. We talked about this kind of situation when we talked about sonograms with the baby and how the waves are go into the uterus and then come back and are reflected back, and that's how you determine the lights and darknesses of the sonogram pictures. So if your car is moving towards the patrol car, the reflected waves have a higher frequency. The Doppler shift depends on the speed, of course. A computer calculates the speed and displays it for the police officer, which obviously then they go after you and give you a ticket. Doppler radar can measure the Doppler frequency shift in addition to the magnitude of the echo signal reflected from precipitation. The Doppler shift is related to the velocity of the precipitation blown by wind either toward or away from the radar installation. So not only can we talk about the Doppler effect with sound, but we can also talk about it in terms of light. So just like with sound, as a light wave moves towards you, the wavelengths get compressed and shorter. This is known as the Doppler blue shift, as you can see in the color of the wave and the people in the picture. As the wave moves away, you have a changing of this shift in color, moving towards the redshift. So as your wavelengths move further apart, you end up with the Doppler red shift. Applying to the color spectrum, we can tell if an object is moving toward or away from us just basing it on its color. If you're interested in studying space, which I know some of you are, the redshift is what actually allowed us to understand that the galaxies are expanding. So when talking about the Doppler shift or the Doppler effect for light waves, again, as light is shifted toward the red, the longer wavelengths, we have a Doppler redshift. As the waves are shifted towards the blue end with a shorter wavelength, this creates a Doppler blue shift. The amount of frequency shift depends on the speed of the source. So the speed of the source is what determines the frequency or the pitch in terms of sound or the color that we are able to see. Some of you may be familiar with this. This is not a heat, like an infrared camera that you would see where you can put it up and see the different heats in terms of like the way that like snakes are able to see. So this is when you, for I can't even speak, for astronomers, the velocity of your sun and the plasma around it, which is similar to fire, just at a very high hot temperature. We're able to see the blue shift as it is moving toward, or the red shift as it moves away, which is how you're able to capture the data for astronomers and be able to study space. So, is there a Doppler effect if a sound source and an observer are moving with the same velocity? The key word here is the same. If you have a Doppler shift, you have to have a change in the speed. So the answer would be no. What would be the effect if a moving source accelerated toward a stationary observer? Well, if you were accelerating toward a stationary observer, obviously you think about you being outside and having an ambulance come towards you. You should hear an increase in the frequency, meaning that you have an increase in the pitch as your speed increases. Astronomers have observed that all distant galaxies appear redshifted. Is this evidence for an expanding, contracting, or stationary universe? Well, we just talked about the fact that if you're interested in space, the redshift is what has allowed us to actually determine that galaxies are moving away. So the galaxy is forever expanding. Traffic radar is based on, obviously, the Doppler effect. That's what this whole thing is talking about. I did post this video on Google Classroom. Definitely check it out. It has to do with shock waves, which is what we were about to talk about. So when the wave velocity is exceeded by the source speed, we have something that is called a shock wave. These are conical wave fronts produced when the velocity of your source is larger than the velocity of your wave, or at a supersonic speed, which is called a shock wave. The formula for this is sine of theta is equal to the velocity of the wave divided by the velocity of the source. And this is what a shock wave looks like. It forms a V-like pattern, as you can see here, again creating a conical shape. So it forms a V-like pattern with spherical wave fronts. This V-shaped wave front produced by a boat when the boat's speed exceeds the speed of the water waves. We see this also when we talk about jets and space shuttles traveling at supersonic speeds that are going to produce shock waves. This is called a sonic boom. That's when you have a loud explosion produced by this phenomenon. A shock wave carries a lot of energy concentrated on the surface of the cone, with corresponding great pressure variations. This is very hard on ears and can damage buildings when aircrafts fly supersonically at very low altitudes.